In this video, we continue our discussion on cryptography, and we are going to talk about digital signatures. So to include your digital signature, the process of signing is that you're going to take the plain text document and you're going to hash it, similar to what we taught you with generating a hash for file integrity. So this is going to create what is called a message digest or a hash. From here, the individual is going to use their private key to sign this hash. So it's now going to have their signature attached to it. And then they have a certificate from a third party that they're going to attach to the data so that someone can confirm that the certificate matches their signature. Then this is going to be transmitted using symmetric encryption to ensure that only the person that is intended to receive it receives the message. And then it is verified by the receiver. So the receiver is going to receive the digitally signed data, and they're going to split out the plain text and run it through the hash function again to see if it generates the same message digest or hash. And then they're going to take the signature, and then they're going to use the sender's public key to decrypt it and see if it generates the same message digest or hash. If the two of these are equal, we can assume that the person did sign their message, proving that this message did come from them. For any ongoing communication, we're going to ensure message-by-message confidentiality or authentication, depending on how the sender and the receiver interact. To ensure confidentiality, the sender is going to encrypt with the receiver's public key, and then the receiver is going to decrypt with their private key. To ensure authentication, the sender is going to encrypt with the sender's private key, and then the receiver is going to decrypt with the true party's public key, not the sender's public key, because the sender could use whatever public key they want to act like this message is coming from them. But in reality, the true party's public key is verified by a third party, so we can ensure that it truly comes from who they say they are. As for HMAC, which are hash message authentication code, which are more widely used than digital signatures because digital signatures consume a lot of processing power and are difficult and expensive to distribute, we can ensure message-by-message authentication, and you'll see here the process is simpler. So the signer is going to take the plain text of the document. They're going to add their key to the plain text. From the two of these combined, they're going to generate a hash function, which is going to create this HMAC. They're going to take the plain text and attach the HMAC to it, and then they'll transmit this using symmetric encryption over to the receiver. The receiver is going to verify it by grabbing the HMAC and the plain text, and they're going to pull out the plain text with the key, and they're going to run it through the same hash function. And then they're also going to take that transmitted HMAC and compare that to the computed HMAC to be able to determine whether the user should be authenticated or not. So this brings us to the word nonrepudiation, which basically means that a sender cannot deny the sending of the message. With digital signatures, it's very difficult to repudiate. The reason being is that you attach your private key to that, and then it's decrypted with the public key. Whereas HMACs are easy to repudiate because we're just using it for authentication rather than to verify that it truly is coming from the individual. So we can overcome this by having digital signatures at the application layer. For example, when you send an email, you can have a digital signature there to verify that the email is coming from you. And then we can have HMACs at the internet layer for packet authentication. And the internet layer is basically about sending packets to and from different networks. And this is just to ensure that the packets are authenticated. In order to ensure that our information is encrypted when we're connecting with networks outside of the internal network, we're going to use what are called VPNs. VPNs are virtual private networks that secure communication over an untrusted network, for example, the internet. And it's strongly encouraged that you use a VPN on any network that is not yours and that you don't have control over, because there could be man in the middle that are imitating the networks or capturing your packets as the network isn't as secure as you would want it to be. So there is a host-to-host VPN where one device can connect to another device. There is a remote access VPN where one device can connect to an internal site. For example, I use Global Protect at Creighton to be able to connect to Creighton's internal network when I need to push out updates to my server. And there is site-to-site VPN when you have companies that are transacting with other companies. We want to ensure our communication is secure between the two sites. So there are various methods to using VPNs. First method is SSL or TLS, where the client is going to communicate with the server. The client only needs a browser, and the server needs to have SSL built into it. So the client is going to send a hello request to the server, and the server is going to say, all right, here's my public key and the certificate that contains information about it and the certificate authority. And then the client is going to verify the certificate and then send a one-time session encrypted key that they're going to be able to communicate. From here, the web server is going to decrypt the one-time session key using its private key to be able to say, hey, we're ready to communicate. And from there, you have a secure connection established between the web browser and the web server. You can also have a gateway in the middle where you're basically doing the same steps, but you're passing it through a gateway just to verify that nothing nefarious is going through the network rather than establishing that communication right away. Alternatively to SSL, we have IP security or IPSec, which advocates for stronger security. It is the gold standard. You'll notice that it has two modes of operation here, which are transport and tunnel. So let's go ahead and look at the difference between these two modes of operation. The first mode of operation is the transport mode. And the way that the transport mode works is that we are going to communicate from our corporate site A to corporate site B, and this is host-to-host security. So I am communicating from my personal computer to a specific server, and this kind of bypasses all the firewalls and gets directly from one device to another device. So an alternative that can be used is the tunnel mode, which provides security through gateways. So essentially, you're going to be able to communicate from gateway to gateway. Once you get to the gateways, it's going to ensure that the traffic is traffic we would expect before passing it onto the internal network. So when you're looking at transport versus tunnel modes, the bottom line is that you have end-to-end security at a high cost with transport mode, because essentially if one person gains access to that device, they have direct access to the specific devices that VPN would have provided. The tunnel mode is low cost, and it protects the packet over the most dangerous parts of the journey to ensure that all your packets are protected. Thanks for watching my video. Feel free to click the links here to watch the next video of the playlist, continue to the next playlist, or subscribe.